Let's prove two results that I kind of talked about last video, but never proved. The first of those is if A is a subset of B and B is countable, then A is either countable or finite. This will justify the claim I was making last video about countable sets being the smallest infinite set. Assume the hypothesis that A is a subset of B and B is countable. If A is finite, we're done, so assume A is infinite. By the definition of countable, there exists a bijection f from the naturals to B. We'd like to describe a new function that's a bijection from the naturals to A. By letting a sub n equal f of n, we could think of f as a function that sorts all of the elements of B into a sequence, where each element shows up exactly once. And since A is infinite, if we just take all of the elements in that list that are also in A and focus only on them, they form a subsequence. So we could define our bijection G from the naturals to A to map each natural n to the nth term in the subsequence. And this new function is definitely one-to-one, because given two indices, say n1 not equal to n2, g of n1 and g of n2 represent two different terms in the subsequence, which correspond to two different terms in the original sequence, where we know each element of B shows up exactly once. So g of n1 is not equal to g of n2. And this new function g is definitely onto, because given, say, an arbitrary element of A, it must occur somewhere in our subsequence, and so say it occurs at an index n, then g of n equals that element. You could define this function g even more explicitly, but I think this is sufficiently convincing. The other result referenced last video was that finite or countable unions of countable sets are still countable. We used this to argue that the irrationals must be uncountable, because if they were countable, then that would contradict the reals being uncountable, since the reals are formed by the union of the rationals and the irrationals. Let's state this theorem in two parts. First, if a1, a2, an are each countable sets, then the finite union a1 union a2 union union an is countable. And second, if an is a countable set for each natural number n, then the infinite union n equals 1 to infinity of a sub n is countable. It won't be true that an arbitrary union of countable sets is countable, because if you form the union of uncountably many of them, you could form an uncountable set. For the proof of the first part, let's start with just the union of two countable sets, and then let's extend by induction to any finite union of countable sets. So let a1 and a2 be countable sets. That means we'll have a bijection from the naturals to each of these sets on their own, and we'll want to form a bijection from the naturals to the union of these sets. This will be kind of similar to showing that the naturals have the same cardinality as the integers, where we needed to map the naturals to all the positive integers as well as all the negative integers in 0. Let's define B2 to be the set difference A2 minus A1, just so that we're working with two disjoint sets. We can observe that A1 union B2 is equal to A1 union A2, but considering a disjoint union, we'll make our argument cleaner. We won't have to worry about the same element showing up in both sets. By our previous theorem, B2 is either countable or finite because it's a subset of A2. So case 1, assume B2 is finite, then we could express B2 as x1, x2, up through xn, just some finite collection of elements. And we know there exists a bijection f from the naturals to A1. So we'll form our new bijection from the naturals to the union of A1 and B2 just by shifting over all of the outputs of f by exactly n, to leave n open slots in which we can fit each element of B2. So I've let n represent specifically the number of elements in B2, so I'll define, say, g of k to equal x sub k if k is less than or equal to n, and to equal f of k minus n otherwise. And this g is a bijection. Now let's consider a case 2. What if B2 is countable? Well, again, we can let f represent a bijection from the naturals to A1, and this time let's let g represent the bijection from the naturals to B2, and we'll construct a third bijection h. Let's define h of n to be equal to f of n over 2 if n is even, and to be equal to g of n plus 1 over 2 if n is odd. And you could also do this the other way with the f on the odd terms and the g on the even terms. But we form this new bijection by alternating back and forth, and we can verify that it's one-to-one, assume h of n1 equals h of n2, and here's where it's convenient that the two sets A1 and B2 are disjoint, and why, if we just applied this technique to A1 and A2 directly, we wouldn't necessarily be guaranteed that our function was one-to-one? Because we can say, since a1 and b2 are disjoint, this number, h of n1 equal to h of n2, lives in exactly one of them. Let's just look at the case where it lives in b2. The other case will be similar. By definition, h of n1 is equal to g of n1 plus 1 over 2, and h of n2 is equal to g of n2 plus 1 over 2. And since g is one-to-one, the equality of these outputs forces those inputs to be equal. So n1 plus 1 over 2 equals n2 plus 1 over 2. So n1 equals n2. And like I said, the other case is similar. So h is one-to-one. In a sense, it inherits the property of being one-to-one from the functions f and g, based on the way it's constructed. To show that h is onto, let's take an arbitrary element of our codomain, a1 union b2, and show that there exists some element of the domain that maps to it. Let y be an element of a1 union b2. So y is an element of one of these. Let's first suppose that y is an element of a1. Then since f is onto, there exists some n in the naturals such that f of n equals y. We can observe then that the specific input 2n is mapped to y. Notice that h of 2n is equal to f of 2n over 2, which is equal to f of n, which is equal to y. You could then instead assume that y was an element of b2 and make a similar argument. So h is onto, so it's a bijection from the naturals to a1 union b2, and so a1 union b2 is countable. And we already said that that's the same set as a1 union a2, and so a1 union a2 is countable. Now let's extend this proof to any finite union of countable sets using induction. For the inductive hypothesis, let's assume that the union of k countable sets is countable. Let's let a1 through ak plus 1 each be a countable set. Let's note that the union of the first k plus 1 of these sets is equal to the union of the first k of them, union ak plus 1. Since each of the two sets in this union are countable, their union is countable by what we just proved. And this step of showing that the statement being true for k implies it's true for k plus 1 completes the proof of our first part, that any finite union of countable sets is countable. For the second part, however, we can't use induction. Let's instead prove it directly. Assume an is countable for each natural number n. It will be easier to work with disjoint sets, so let's let b1 equal a1. Let's let b2 equal a2 minus a1. Let's let b3 equal a3 minus a1 union a2. And in general, let's let bn equal an minus the union of a1 through an minus 1. And we can note that the countable union of all the an is equal to the countable union of all the bn. But we have the convenient property that the bn are pairwise disjoint. Now each of the bn is guaranteed to either be finite or countable. And so instead of going through a whole re-indexing process to try to sort out the countable sets from the finite sets, we'll just leave them all mixed together. And then instead of producing a bijection from the naturals to our union, we'll just produce a bijection from a subset of the naturals to our union. For each index n, since bn is either finite or countable, there exists either a bijection from the naturals to bn, or a bijection from some finite set, 1 through kn, to bn. And yes, bn could be an empty set, in which case this would be a trivial bijection from nothing to nothing. In order to visualize how we'll assign the new indices, let's rearrange the naturals into this two-dimensional array by zigzagging down and right as we write out each natural number in increasing order. The rule for the path to follow in constructing this array would be twofold. If you're in row 1, return to column 1 and start a new row. Otherwise, move up and right. Now let's define our new overall bijection f from a subset of the naturals to the countable union of all of the bn. Given an input n, let I and j represent its row and column index in this array, respectively. Then define f of n to equal f sub I of j, if it is defined. In other words, your row index determines which function to use, and your column index is the input to that function. The reason it might not be defined is because some of the functions only accepted indices up to some finite cutoff as inputs. So this is a function from some subset of the naturals to our union of all of the bn. And this will be a bijection, inheriting the properties of being one-to-one and onto from each of the fn, and from the fact that the bn are pairwise disjoint. And by our first theorem, a subset of a countable set has to be either finite or countable. So the domain of this function has to be either finite or countable, which implies that our union is either finite or countable. But we know our union isn't finite because, say for instance, B1 is a subset of it, and B1 was exactly equal to A1, which was taken to be a countable set. So the union of all of the Bn has to be countable, and that union was exactly equal to the union of all of the An, so that has to be countable as well. And so this proves our part 2, that countable unions of countable sets are still countable, and so that completes the proof of this theorem. At the end of last video, we had a discussion about sizes of infinity. And at the start of this video, we proved that there is a smallest size of infinity, being countable. But there's no largest size. And this is not necessarily an obvious result. To prove this, let's define a power set. Given a set A, the power set of A, denoted P of A, refers to the set of all subsets of A. So the elements of the power set are the subsets of A. For example, if A was the set of 1, 2, and 3, then the power set of A would contain 8 elements: the empty set, the set containing 1, the set containing 2, the set containing 3, the set containing each pair, and the set A itself. And it's not hard to notice that in the finite case, the power set is always larger. Specifically, if the cardinality of A equals n, then the cardinality of P of A equals 2 to the n. The justification for this is that given a finite set A, every subset of A, every element of the power set, corresponds to exactly n decisions on whether or not to include each element. And there's 2 ways to make each of those decisions, and they're independent of one another. So there's 2 to the n possible ways to make that set of choices. Cantor's theorem states that this property of the power set being larger is true in the infinite case as well. Given an arbitrary set A, there does not exist a function from A onto the power set of A. This is our infinite notion of the power set of A being larger. It's impossible to map A onto the power set of A. And an immediate but profound consequence of this is that there's no largest set. There can't be any universal set, because you could always just take its power set and come up with something even larger. The proof of this statement will be an indirect argument. And before we write it down in symbols, let's consider an anthropomorphized version. Given infinitely many people, it will always be possible to form more committees from those people than there are people themselves. And we're considering literally every possible committee. It could be the empty committee with no one on it. It could be the committee of all people whose name starts with A. It could be the committee of everyone. And there could be infinitely many people. Now, let's say there was a way to name each committee after one person so that nobody's name was reused. And the committee naming would be kind of arbitrary. It wouldn't matter whether you were on that committee or not. The names would just all be assigned to committees. Well, since we formed every possible committee, there's going to be one committee containing exactly all of the people who aren't on the committee named after them. And suppose that committee is named Deborah. Is Deborah on that committee? This is where the contradiction arises, because if she is, then she's on the committee named after her, and so she shouldn't be. And if she isn't, then she's not on the committee named after her, and so she should be. Returning to the land of symbols, we can write this proof as a contradiction argument. Assume there exists a function f from A to the power set of A that is onto. So every subset of A is equal to f of A for some little a. This is like the committee named after little a. Let B be the set of all A in A, such that A is not contained in f of A. But since f is onto, there exists, say, some specific x in A, such that f of x is equal to B. So is x in B? If it is, then it isn't, and if it isn't, then it is. So it's a contradiction, and that proves Cantor's theorem. In the next video, we'll look at the Cantor set, a very bizarre construction.